The world is rapidly embracing fifth-generation technology. This new generation of wireless communication promises lightning-fast speeds and unprecedented connectivity. Behind the scenes, passive components play a crucial role in making this possible. These components may not be as glamorous as their active counterparts, but they are essential for the proper functioning of any wireless system. Passive components are the unsung heroes of the wireless revolution. They are the silent partners that enable the transmission and reception of data over the airwaves. Without them, our smartphones, laptops, and other wireless devices would be nothing more than expensive paperweights. In this essay, we will delve into the world of passive components and explore their significance in fifth-generation technology. We will examine their various roles, their evolution over time, and the challenges of integrating them into increasingly complex devices. By understanding the critical role of passive components, we can gain a deeper appreciation for the complexity and ingenuity of modern wireless communication systems. These often overlooked components are fundamental to the continued growth and development of the connected world. Passive components are the building blocks of any wireless system. They are electronic components that do not amplify or generate signals, but instead manage and shape the flow of electrical energy. Unlike active components, they do not require an external power source to operate. These components perform a wide range of essential functions, including impedance matching, filtering, tuning, and biasing. Impedance matching ensures that signals are efficiently transferred between different parts of a circuit. Filtering removes unwanted frequencies from a signal, preventing interference. Tuning adjusts the frequency response of a circuit to optimize performance. Biasing sets the operating point of active components, ensuring they function correctly. Each of these functions is critical for the proper operation of a wireless system. Common types of passive components include resistors, capacitors, inductors, and antennas. Resistors limit the flow of current. Capacitors store electrical energy. Inductors resist changes in current. Antennas transmit and receive electromagnetic waves. Together, these components form the backbone of modern wireless communication. The advent of fifth-generation technology has brought about significant advancements in passive component technology. Sub-6 GHz fifth generation, which operates at frequencies below 6 GHz, relies heavily on discrete lumped circuits. These circuits consist of individual passive components connected together on a printed circuit board. Over time, these components have become smaller, more efficient, and capable of handling higher frequencies. Miniaturization has been a key driver of innovation, allowing for the development of increasingly compact and powerful wireless devices. Another important trend has been the development of high-frequency materials and fabrication techniques. These advancements have enabled the creation of passive components that can operate at the high frequencies required for fifth generation. Improved materials also reduce signal loss and improve overall system efficiency. The evolution of passive components for sub-6 GHz fifth generation has been essential for meeting the growing demands for faster data rates and greater network capacity. As fifth generation technology continues to evolve, we can expect to see further advancements in passive component design and miniaturization. Section 4. Advancements in distributed components for mmWave 5G. Millimeter wave, or mmWave 5E, operates at much higher frequencies than sub-6 GHz 5G, typically between 24 and 100 GHz. These higher frequencies offer the potential for even faster data rates and lower latency. However, they also pose significant challenges for passive component design. At mmWave frequencies, the wavelength of electromagnetic waves is extremely small. This makes it difficult to use traditional, discrete lumped circuits, as the size of the components becomes comparable to the wavelength. To overcome this challenge, designers are turning to distributed components. Distributed components are essentially transmission lines that are designed to exhibit specific electrical properties. These components are fabricated using advanced microfabrication techniques and can be integrated directly into the PCB or even within the package of a chip. Examples of distributed components include microstrip lines, coplanar waveguides, and substrate integrated waveguides, or SIW. These components offer several advantages over traditional lumped elements at mmWave frequencies, including lower loss, better impedance matching, and improved integration capabilities. Section 5. Antenna systems in package. The key to 5G connectivity. Antennas are essential components of any wireless system, responsible for transmitting and receiving radio waves. In 5G devices, antenna design plays a critical role in ensuring reliable connectivity and optimal performance. The trend towards smaller and more integrated devices has led to the development of antenna systems in package, or AIP. AIP technology integrates the antenna directly into the package of a chip, reducing size, cost, and signal loss. Various types of antennas are used in 5G AIP, including phased array antennas, patch antennas, and dipole antennas. Phased array antennas consist of multiple antenna elements that can electronically steer the beam of radio waves, improving coverage and reducing interference. Patch antennas are small, flat antennas that are easy to integrate into packages. Dipole antennas are simple and efficient antennas that are well suited for mmWave frequencies. The choice of antenna type depends on the specific requirements of the application. Section 6. High-precision patterning enabling heterogeneous package integration. The integration of multiple components, including passive components, antennas, and active chips, into a single package is crucial for miniaturizing 5G devices. This heterogeneous package integration requires extremely high-precision patterning techniques. High-precision patterning refers to the ability to create extremely fine features on a substrate, such as a silicon wafer or a PCB. These features are used to define the electrical connections between different components and to create the structures of passive components like filters and antennas. Advanced lithography techniques, such as extreme ultraviolet or EUV lithography, are used to achieve the required level of precision. These techniques use light with extremely short wavelengths to create features that are just a few nanometers in size. High-precision patterning is particularly important for the RF front-end, or RFFE, which is the part of a wireless device that handles radio frequency signals. The RFFE typically includes a variety of passive components, such as filters, duplexers, and impedance matching networks. Section 7. Conclusion. The future of passive components in 5G and beyond. Passive components are essential for the proper functioning of 5G and future wireless communication systems. They play a critical role in managing and shaping the flow of electrical energy, ensuring signal integrity, and enabling efficient transmission and reception of data. As wireless technology continues to evolve, the demands placed on passive components will only continue to increase. Future wireless systems will require even higher frequencies, greater bandwidths, and lower latency. To meet these demands, we can expect to see continued innovation in passive component design, materials, and fabrication techniques. The development of new materials with lower loss at high frequencies, the adoption of advanced 3D packaging techniques, and the exploration of novel component architectures will be key areas of focus. The future of wireless communication depends on our ability to continue pushing the boundaries of what's possible with passive components. These unsung heroes will continue to play a vital role in shaping the connected world for years to come.